Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. On. In this tutorial video, we'll go through this November 2015 paper 2 variant 1 for the Cambridge International 16 to 18 years old A-level curriculum. In this first question, we have aluminium. Aluminium is very clearly a metal in period 3. These days we use the term group 13 for the new specification from 2016 onwards. And we are asked to describe the structure of solid aluminium. So we know that it has a giant metallic structure. So as a solid, you will have particles tightly packed together. You got to define and specify what kind of particles that is. So we first talk about the structure first, giant metallic structure. And what does the giant metallic structure consist of? It consists of aluminium cations that you get after you shed away, after you lose your outer shell electrons. So you get aluminium cations, Al3 plus, in a sea of delocalized valence electrons, because that is what you do as a metal. You shed away your outer shell, your valence electrons, and it is that electrostatic force of attraction between the valence electrons as well as the positively charged cations that result in the strong metallic bond. So what else can I say? Sea of delocalized valence electrons, that's pretty much it really, I can say. What else can I say? I think the idea of solid there is that I have to talk about solid particles as well. So in the solid state, the particles, in this case the ions, the cations, they are arranged like in a layered structures. They are tightly packed. So this is a little bit of states of matter as well. We just don't want to lose any mark at all. They are tightly packed in a fixed position, so they are not free to move at all. However, metals does conduct electricity, not because of the cations as they don't move. It's the delocalized valence electrons that are delocalized and therefore they are free to move around. In part B, a common use of aluminium is to make as conducting cables. Obviously, they conduct electricity. So suggest two properties of aluminium that make it suitable for this use. This is straight from the 14 to 16 years old IGCSE, GCSE or O-level curriculum as part of the uses of aluminium. I think these days in the new specification, we don't talk too much about the use of aluminium anymore, as they've taken out the extraction of aluminium from aluminium oxide from the A-level AS syllabus. But regardless, it's still a very good question. I mean, we talk about the light weight or light density or the low density. Light, low, that should be all right. Light or low density of aluminium is also the primary reason why you use aluminium as a major component to make a aircraft body. So it's light. And then the other one is that it has high conductivity. So across the third period, we know sodium, magnesium, and aluminium. Aluminium is the best conducting as it can delocalize the greatest number of valence electrons, giving the Al3 plus cations there. Okay, straight to the point there. Now the cables are attached to pylons by ceramic support. Again, ceramic material was from the 2015 syllabus and it has since been taken out. But ceramic materials must have giant structure. So we don't care about, it's not necessarily one particular type of giant structure, because it could have giant ionic, it could even be giant molecular, because the type of materials that are considered ceramic, SiO2, what else, MgO, if I'm not mistaken, Al2O3 as well. So must have giant structure that can withstand high temperature, because they don't melt or boil easily. Okay, high temperature. So your electrical cables carry electricity. Sometimes you get heating up due to a power surge, and you don't want these things to melt easily or to boil easily, right? So they have high melting point. They don't melt easily. They have high melting point. They don't melt easily. That is saying the exact same thing there. Okay. Well, I guess actually they don't melt easily must be the next part of the question, because what makes it suitable for this use, they don't melt easily. Whereas describing the structure of ceramic materials, so must have giant structure, that's probably the way to get around these two questions here. But just take note that ceramic was already taken out from the syllabus from 2016 onwards. Now the next thing, aluminium reacts with chlorine to give you this white solid chloride. This is part of period 3 chloride chemistry under AS periodicity. So this is still in the syllabus, obviously. All right. Describe the structure and bonding, and then suggest how it explains the low sublimation temperature, solid going to gas. So the low sublimation temperature suggests that you must have a simple covalent structure. That's the only structure that will have low melting and boiling point, because you would just be breaking the weak intermolecular forces between the molecules. So the low sublimation temperature straight away suggests to you it must have simple covalent structure or simple molecular structure, both of which are accepted by Cambridge, obviously. Suggests that the solid chloride has simple covalent structure. And when you have simple covalent structure, what do you break when you have to boil it or melt it? So we talk about sublimation. So what I can say is, so sublimation only need to break. So there's solid going to gas, only needs to break or overcome weak intermolecular forces. We have to use all the right and the correct adjective in order to describe this thing, so that we don't lose any marks at all. And this intermolecular means between the molecules, but it doesn't hurt to add in this idea that this intermolecular force of attraction is not inside the molecule, it's between the molecules there. So if we only need to break that weak intermolecular force of attraction, so this doesn't require a lot of energy. This does not require a lot of energy. So the very idea that we need to relate energy expenditure with how easy it is to melt or boil, or in this case sublime, is going to be how you explain it fully, and not just stopping there without making a qualifying statement usually. The next question, calculate the empirical formula. So this is defined as the simplest whole number ratio of atoms. Simplest whole number ratio of atoms. Straight away from your O-level or GCSE or IGCSE level chemistry, we have 79.7% of chlorine. This is percentage, and percentage is out of 100%. So this is called mass per 100 gram, because it's essentially the breakdown of the percentage. If you have 79.7% of chlorine and you are a chloride of aluminium, therefore your remaining percentage must be the other atom, which is aluminium. So 100 minus 79.7, I get 20.3. So going back to that, if I have mass, I need to work out my mole. So my mole there is mole of the atoms. So I need to go to my periodic table. So in the new 2022 syllabus onward, your periodic table will no longer be on a separate data booklet. They'll be inside the question paper itself. So, learn to cope with that. Aluminium, 27.0 is the relative atomic mass. And then I am doing relative atomic mass because of the definition, simplest whole number ratio of atoms. So I don't do the molecular mass at all. So 20.3 divided by 27.0. I get 0.752. 79.7 divided by 35.5, I get 2.25, like that. So what next? Well, I need the simplest ratio, right? Because it's the simplest whole number ratio of the atoms, so the aluminium and the chlorine. To get the simplest whole number ratio, you need to divide by the smallest number, which in this case is 0.752. So that divided by itself is 1. That divided by 0.752, that gives me 2.99. Simplest whole number ratio of the atoms, AlCO3. Of course, as you know it, trigonoplanar geometry, 3 bond pair, 0 lone pair, they repel equally, the 3 bond pair repel equally. what you get is trigonoplanar. This is as stated in the VSEPR, valence shell electron pair repulsion theory from AS chemistry, structure and bonding, shape of molecule there. And the next bit is this sample of this chloride, meaning to say in the vapor phase, in the gaseous phase, they occupy this much volume. And they give you the temperature and the pressure. It seems like this is an ideal gas equation kind of thing. In our ideal gas equation, P equal to nRT, and that N refers to mass over mR for the gas. If I want the mR, I have mRT over PV. It's always been my habit in all my tutorials, and you can see this from the topical playlist, that I rearrange to get what I want, and then I write down all the detail on the side instead of wasting time putting them in. I clarify everything on the side so that I'm not making any mistake when I key in my calculator. 8.31 joule per Kelvin per mole or joule per mole per Kelvin is stated in the data booklet, which of course now will be provided in the question paper itself from the 2022 syllabus onward. The temperature of the gas must be in Kelvin. This is in degrees Celsius given there, so I have to add it with 273 and get 473 Kelvin. My pressure is in kilopascal, so I have to convert this to pascal by multiplying by 1000, so times 10 to the 3 pascal. The very last thing, which is a bit tricky, is this volume here is in cm cube. So you know, if our volume is in cm cube, we think about 1 cm is 1 divided by 100 meter, because you convert cm to meters like that. So I can think of my indices 10 to the minus 2 meter. If you cube both sides, because that is what primary school mathematics will have told you, equal mean whatever you do on the left, you do it on the right. So when I cube both sides, I get 1 cm cube. 10 to the minus 2 cube, your mathematics will have told you, that's 10 to the minus 6. So to convert cm cube to meter cube, I need to multiply by 10 to the 6. So the volume there is 200 times 10 to the minus 6 meter cube. I better write down the unit properly, otherwise I'll make a mistake. I've got all of these in the correct units now. I've got the expression, so I don't really need to write them down again. I already done the hard work. I already specified to the examiner I know what I'm doing. I just need to press my calculator now. 1.36 multiplied by 8.31 multiplied by 473 divided by 100 times 10 to the 3 divided by 200 times 10 to the minus 6. Make sure you know how to key this into your calculator, obviously. And if you get a silly number in the end, they want 3 significant figure, so you know, I'm just gonna show it to 4 first. So 267.28, there's 5 significant figure, but last but not least, you want it to 3 significant figure. So that's it really. 267 my final answer there. So 267 as required, 3 significant figures. To get the molecular formula, we know the MR of the empirical formula multiplied by a certain factor. Will give us the MR of the molecular formula. So our empirical formula just now was AlCl3. So if you go to the data booklet, your periodic table, 27.0 plus 35.5 times 3, I get 133.5 times a factor, let's say x equal to 267. So that looks like it's a multiple of 2. And if that is the factor, 2 is not the answer because they want the molecular formula. Definition of molecular formula is stated in the AS syllabus. It was also stated in your year 9 chemistry when you were 14 to 16 years old during the O-level, IGCSE or GCSE level chemistry. So it's Al2Cl6 because you got to multiply the empirical formula by a certain factor. So there are 2 of that and there are 6 of that, as you have 2 multiple lots of this empirical formula. Al2Cl6 is a case study under your dative covalent bonding part of the syllabus, and what you can do is you must be able to draw. You must be able to draw because they can ask you to draw the dot and cross of these, and before you do the dot and cross, you need to be able to do the display formula so that you know which one is the dative covalent bond, and that is what I've done there. There's the dative covalent bond, the pink one there, and the rest of them, they are all the normal covalent bond. When you convert this to dot and cross, you will have 2 lone pair remaining on these 2 chlorines because you have used one of these lone pair on each chlorine to form dative covalent bonds. The arrow comes from the donor to the acceptor. The one with the lone pair donates both the electrons to this aluminium with the empty orbital, As aluminium is in group 13, only 3 valence electrons. Just now, you had trigonoplanar geometry because you have 0 lone pair and 3 bond pair, since aluminium has only 3 valence electrons there. So everything kind of linked together. When you draw the dot and cross, also do not forget that there are 3 lone pairs on these other chlorine and 2 lone pairs on these chlorines. And yeah, make sure you know the dative covalent bond, that you don't show a dot and cross, you show both the electrons coming only from one of the atom, as defined in AS, dative covalent bond, also known as coordinate bonding. Okay, that's the end of that 13 mark. Very nice first question here.